All right, I think I'm recording it now. So in this tutorial, we will talk about Numpy and Pandas, because those are two basic libraries that you will use a lot in machine learning. You may also notice that a lot of time in this class we will use sklearn. We may also use PyTorch or some other machine learning libraries, but Numpy is the most basic library that every one of you should learn how to write code with. So Numpy is it's basically a library for you to play with matrices or tensors. The basic component of Numpy is an object named ND-array. ND-array is basically a multi-dimensional vector, or you should say a matrix or a tensor. So to use that, you would need to first install Numpy if you haven't installed it already, but in my system it's already installed, so I don't have to install it again. You can do that with pip install Numpy. And after you import Numpy, you can create an ND-array like the following way. You can do numpy.array and then feed a nested list to it. You can just pass a list if you want to. Let's say 1, 2, 3. Then you will get an array. When you see it, this is if you check the type of A, it will show you that it's a NumPy ND array. ND means n-dimensional array. And you can check the shape of the array by a.shape. And you see the shape is 3 because there are 3 numbers in this ND array. You can also, since it's an n-dimensional array, you can also create a bigger shaped array. Let's change the nested list to be, it's a list of lists, 1, 2, 3, and 5, 6, 7, 8. Let me just write more numbers here. 1, 2, 3, 4, 5, 6, 7, 8. Now this is another ND array, and if you check the shape of it, it's 2 times 4 array. And there are some other ways to initialize an ND array. For example, if you want to initialize an array with all zeros, then you can create it by np.zeros and pass in a shape. A shape is a tuple. It could be, let's say this will give you a 2 times 4 0 array. You can even make bigger arrays by typing multiple numbers, and you will have higher and higher dimensional arrays. This is a huge array, actually. So you just pass in a tuple, and it will give you a desired shaped array. And you can, there are zeros, there are also ones, and these are all initialized with ones. And you can, you may also use np.random.rand. This will give you any numbers between, this will give you numbers between 0 and 1. And note that in this case, you don't have to pass in a tuple. I don't know why, but it seems like NumPy has different conventions to initialize arrays. And this will give you numbers between 0 and 1. And you can also randomly generate standard Gaussian distributions. So these will be numbers centered at 0 with standard deviation of 1. You can also initialize a range of numbers. For example, numpy.a range 100. Then you will get numbers from 0 to 99. And you can reshape it. You can always reshape an array to an ideal, to what shape you want to get. For example, if you want to change the shape to 10 to 10, then you'll get a 10 to 10 array. Note that if you observe the array, you see that it has both rows and columns. And it just changes the shape to be 10 rows and 10 columns. And you can also make it another shape. For example, 4 times 5 times 5. Just make sure that those numbers match. 4 times 5 times 5 is equal to 100. So let's make that be. All right, so these are, so you can create arrays, ND arrays in this way. And if you want to access some specific elements of the ND array, you can just use some more advanced indexing than Python lists. For example, A is a ND array, and you can get a specific element by, let's say, A11 will be the first row, first column, so it should give you 6. Let's see, A is this ND array, and A11 is 6, and you can also do -1, it should be 8. So you can access them in this way, and you can also use array slicing. For example, if you want to get anything up to the first row, anything up to the third column, then this will give you a subarray. With those index slicing, with this technique of array slicing, you can get a subarray from a bigger ND array. You can also get some elements out of the array by specifying the indices of each column, of each dimension. For example, if you pass 1, 0, 1, say 1, 2, 3, then this will give you 6, 3, 8. What's happening here is that you're passing in the row indices as 1, 0, 1. So it will give you numbers at position 1, 1, 0, 2, and 1, 3. So 1, 1 is 6, and 0, 2 is 3, and 1, 3 will be 8. So that's why you get an array of 6, 3, 8. A very useful technique is called Boolean indexing. Boolean indexing is that you can pass in Boolean values to get the values that you want. For example, if you check a less than 5, it will give you those Boolean values. It basically gives you all the positions. It tells at each position, is it true or false? So if you check a less than 5, you see that all those numbers in the first row will be true, and the rest of them will be false. And with that Boolean indexing, you can directly passing that Boolean indexing as the indices to get the values that you want. So now this will give you 1, 2, 3, 4. If you change that to 6, it will give you 1, 2, 3, 4, 5. So that's just an advanced way to filter out the values that you want. So you may be wondering, why are we talking about NumPy ND array so far? They seems pretty reasonable, but why is that useful in, for example, machine learning? The advantage of using ND array is that it implements a lot of mathematical operations in a very efficient way. So some of those mathematical computations will be element-wise computation, dot product, matrix multiplication, sum, mean, max, minimum, and concatenation. Let's just talk about them one by one. So element-wise multiplication will be like this. So we have an array A. It's of shape 2 times 4. Let's just randomly initialize another 2 times 4 matrix. So B and A has the same shape. If you check A dot shape and B dot shape, you'll see that they are of the same shape. And if you add A with B, if you add them up, then it will perform element-wise addition. If you check the values, you will find that the corresponding positions will be added up. So for example, this position is 8 plus 0.2 something, then 8.205, etc., etc. And similarly, you can do element-wise multiplication. A multiplies B, A minus B. This is not very surprising. You can also do A divided by B. And I believe in, okay, that's all. Yeah, you can do those element-wise computations. One very useful feature in NumPy is that it does something named broadcasting. So what's broadcasting? Broadcasting is like, let me just give you an example. If I want to add 2 to each element in the ND array A, then you can directly write A plus 2. This way you get each element added by 2. So if you check the original A, after you add by 2, all the elements is increased by 2. And you can also do A minus 1, nothing, or something else. So how does broadcasting work? Let me just give you some more examples. If I multiply by, let's say if I have another array, let me just name it x equal to numpy.a range 4. So you see x is of shape 4, and the a is of shape, if I type a.shape, a is of shape 2 times 4. If you add a with x, then what will happen is that x will be added to each row of x. So if you do a plus x, you see that's the first row. It's originally 1, 2, 3, 4. And after you add 0, 1, 2, 3, it becomes 1, 3, 5, 7. And the second row is also added by the same row, x. And let's try another example. If I have another ND array, let's say AP numpy.a range 2, y is of shape, y is obviously of shape 2. If you do a plus y, this will give you an error because it says these two shapes are not compatible when you broadcast them together. So what you should do is if you reshape it to 2, 1, you see that the array becomes like this. So it has 2 rows and 1 column. And now you can add them. You see that y has been used as columns to be added to each value of a. Let me just remind you, a is of those values. And then y will be added to each column of a. So the rule of the way how broadcasting works is like following. There's a this is how it works. If you have 2 different arrays, if you have 2 different ND arrays with those kinds of shapes, these will be the results. There are some of those examples. If it's 20, if it's 255 times 255 times 3 with an ND array of shape 3, then this 3 will be repeated so many times to the last dimension, basically. So it will be added as the last column. Should I name it? Should I call it column or row or whatever? It will just be added to each replication of the last dimension. And for this example, if it's 8 times 1 times 6 times 1, the way it works is that if there are dimensions of 1, it can be repeated many more times and then added up. So the rule is that if some dimensions doesn't exist in previous in a smaller dimensional vector, then you should repeatedly prepend 1 before it, and then repeat it as many times as necessary to make the size match. And for the second example, A and B, what happens is that all those dimensions with value 1 will also be repeated so many times so that they will match. So this also matches. This also matches. But remember that let's say if you have two ND arrays with one ND array is of 5 times 4 and the second ND array is of 2, then it won't match. It has to be 1 or exact match. If this B ND array here is of shape 4, it also matches because it can prepend a 1 before it and repeat it 5 times, so they still match. There's a picture showing how it works. If you do NP A range 3 plus 5, then 5 will be repeated 3 times, and you can add them up. And here, for a 3 times 3 matrix plus 0, 1, 2, it will also be repeated as 3 rows. And if it's the following example is interesting. Let me just copy those code here. So if you do np.a range 3 dot reshape 3 1 plus numpy.a range 3, you should notice that the first element, the first ND array is of shape 3 times 1, and the second ND array is of shape 3. And with broadcasting, it will be converted into 1, 3. And then those two, an ND array of shape 3, 1 plus an ND array of shape 1, 3 will be, both dimensions will be repeated 3 times, so it will be of shape 3 times 3. And if you check the result, it will be like this. If it doesn't make a lot of sense to you, you should think about, you should think again, take some time to think about how the broadcasting rule works. So to summarize, the broadcasting rule works in a way that it will prepend 1 if the size does not match. And if in a particular dimension, one ND array is of shape 1 and the other is of shape bigger than 1, then the 1-shaped ND array will be repeated as many times as necessary to make them match. And then it will just do element-wise calculation. All right. Now let's talk about some other operations. Let's say you have A. If you want to expand the dimension, for example, sometimes you want to change the shape of the ND array. Now it's of shape. Now if you check the shape of A, it's of shape 2 times 4, but you can always reshape it as we have done before. You can reshape it to 4 times 2. The way it works is that the order of those numbers doesn't change. It's still 1, 2, 3, 4 all the way to 8, but it's reordered it's reorganized in a different row and column counts. And if you want to add one dimension somewhere in the middle, let's say if you want to make it a 3-dimensional vector, I should say 3-ordered. Let's say someone asked a question, if I want to represent a vector, should I use reshape to make it have n rows instead of n columns? It's up to you. So if you want to make a vector, so NumPy actually doesn't care about whether it's vector or matrix or whatever. As long as your implementation is consistent, then it doesn't matter. If you're doing vector, let's say if you're doing vector addition, then you can either implement it as rows or as columns, but as long as they are consistent, it will be fine. If you want, sometimes you want to add an extra dimension. Now you can do it in this way. We saw that A dot shape is 2 times 4. Note that if you do, although here, if after I do A dot reshape, it returns a new ND array. So if you check the shape again, it's still of shape 2 times 4. This A dot reshape will return a new ND array. And if I want to add an extra dimension, I could do reshape 4, 1, 2. This will give you an extra shape, although it looks like pretty much the same, but it adds an extra dimension in between. You could also do it in this way. You can we can use array slicing. If you do this slicing, it gives you the exact matrix we had before. But if you add one extra non-dimension in the middle, it will also, wait, what happened here? Okay, sorry, I should change it to 2, 1, 4. In this case, so those two operations are the same. If you just specify a non-dimension anywhere in this array, it will give you an extra dimension. It expands the dimension by 1. So if you check the shape of this ND array, it just gives you 2 extra dimensions. Sometimes it's very useful. Okay, you can sum all those values in this matrix by a dot sum. It basically sums up all the values. So 1 plus 2 plus 3 all the way to 8 will be 36. And you can also do, you can actually do row-wise summation or column-wise summation. So it works in this way. You can do numpy.sum a. So these two operations are the same. You can either do a.sum or numpy.sum a. If you do numpy.sum a, axis equal to, axis specifies which, along which axis you want to do the summation. If you say axis is equal to 0, let's recall that a are those values. If you sum over the 0th axis, then it will become 6, 8, 10, 12. So it adds up the values on each column. So the way it works is that you know, a is of shape 2 times 4, and the 2 side is the 0th axis, and 4 columns will be the first axis. And if you sum up over the 0th axis, it will make the 0th axis disappear. It basically sums over those columns. And if you sum over numpy.sum a axis equal to 1, it will sum over the rows, because rows are the first axis. So it will sum over that. And the same thing works for a lot of other applications, operations. For example, max. If you do numpy max a, it gives you the max element, but it can also do row-wise or column-wise max. If I specify the axis equal to 1, then it will give you row-wise maximum value. And if you specify the axis to be equal to 0, you will get column-wise maximum. And same for minimum. You can also check for minimum, which will be more or less the same. Another very useful operation is matrix multiplication. Let's say if you have, I have A is of shape 2 times 4. Let's say I create another random array 4 times of shape 4 times 3. So if you know something about linear algebra, you know that a 2 times 4 matrix times a 4 times 3 matrix will give you shape 2 times 3. So NumPy also implements that. You can do matrix multiplication A and F. Then you get an array of shape 2 times 3. That follows exactly how linear algebra works. And you could also do, so if you do matrix multiplication F and A, it should give you some error because the shape doesn't match. So the columns of the first, let's say the rows of the column number of the first matrix has to be equal to the row number of the second element, right? Yes, I think that's correct. And it just follows how matrix multiplication works. And you can do the same thing with dot, numpy.dot a f. You'll find that they work the same way. So in some cases, like in this case, matrix multiplication and dot product will be the same. But they do have some differences, and I don't want to get to the details here. If you're interested, you can read the documentation by yourself and learn more about it. So these are the basic operations of NumPy. You can do a lot of things with what we have discussed so far already. So I would suggest that for all these assignments in this course, you should always try to implement with NumPy. You should try to implement a lot of things with NumPy if you can. I know that for a lot of operations like matrix multiplication, you may consider doing a for loop. You probably think that I can write a for loop to do matrix multiplication by myself. For example, you can do something like for I in range a dot shape. You can get the last shape. You probably think that I can do dot products by myself. Dot product equal to 0, and then you can do dot prod plus equal a. Let's say a. You want to get the, so a is of shape 2 times 4. You probably think that you can do dot product by assigning. It will be quite complicated. So you do have rows and columns for j in range a b dot shape 1, and then for k in range, let's just do that, a dot shape 1. Then dot product ij plus equal to aik times bkj, something like this. You can do numpy dot zeros. We've talked about zeros before, and a dot shape 0 and b dot shape 1. Sorry, it should be f. I was talking about f all the time. You can certainly do it in this way, and I think it should give you the same result as we did before, dot product. So these two values are the same. So you can implement those loops by yourself if you want to, but you will quickly realize that you will figure out that your implementation is very inefficient because NumPy, I think it's written in C. So if you call those APIs from NumPy, it will be much faster compared to implementing it by yourself. This example is trivial. You probably think that it's so simple, why would I write those 2 for loops by myself? But you will realize that in some of the course materials later, sometimes it's not very easy to figure out how you can do that in NumPy matrix multiplication. But I would suggest that you always try to implement it by matrix multiplications rather than implementing those nested for loops by yourself. It will be highly inefficient. So let's do an exercise. Let's try to do an exercise. We will implement a softmax function. So let me remind you what is a softmax function. A softmax function is like this. If you have numbers, let's say if you have numbers 1, 2, 3, 4, 5, and if I want to convert that to softmax, what happens is that you want to exponentialize every number. You want to get the exponential of every number, sum them up, and then use that as the denominator. Use the sum of the exponentials as the denominator, and the numerator will be exponential of that value. So it follows the equation I defined here. But let's consider a more complicated case. Let's consider if you have a 2-dimensional vector. If you have x equal to numpy.random.rand20 reshape for 4 times 5. So this is an and I want to make the number slightly bigger, so it's more difficult to deal with. So you have such an array, and we consider each we consider to normalize each row with the softmax function. You know, after you apply softmax to each row, the sum of each row will become 1. And this is a way, in a lot of machine learning models, you will use the softmax as a way to normalize the data and get a probability distribution. So let's just think about if you are going to implement softmax in NumPy, how would you do that? So we can, you may think about, you should certainly do numpy.exponential. You can do numpy.exponential. This way you get, what happens is that it will do element-wise exponential. But the problem we see here is that those numbers are just too big. If you guess the exponential of each value, you will get infinity. You get data overflow. So we could think about how can we optimize, how can we do something to avoid the data overflow problem. So if you observe this function, you realize that if I divide the numerator and the denominator by the same value, the results doesn't change. So what I'm suggesting here is that you can divide each value by, you can divide each element in this equation by a constant c, and that won't change the result. And if we take a step further, you will realize that divide an exponential by a constant value c is equivalent to minus the value that you want to get the exponential of. So all those three equations will give you the same result. So we could implement our softmax function in this way. So what I'm going to do is I want to subtract some value from each of the original xi, such that they won't be too big. So what value do I want to subtract? I could subtract the maximum value of each row. Why would I want to subtract the maximum value of each row? Because that way, if I subtract the maximum value of each row, all those numbers will be below 0. So that, and after every number becomes below than 0, then exponential of that number will be less than 1. So we don't have those data overflow problem. So I'm just going to do that. I'll do x1 equal to x minus x dot max 1. So what happens here is that if I write code in this way, you will get some broadcasting error. Because if you do x dot max 1, it's essentially equal to x is equal to 1. So you're going to get the max value of each row, because x is 1 means row-wise maximum value. So if you do that, you will it will tell you that they can't be broadcasted together because these two shapes doesn't match. Why they don't match? Because NumPy realized that the dimensions of two vectors the shape of those two vectors of those two variables doesn't match. So it will prepend 1 in front of the second matrix, and shape 4, 5 and 1, 4 doesn't match. So that's why you can't do subtraction. So what you can do is you can keep the dimension by specifying a parameter. So this way, you get a column. You get column-wise matrix. You get a column of the second of the max values. And if you check the shape of it, it will be 4 times 1. So this way you can do. Now it works. Now you just have all those values changed. You can check whether it actually works. So this is the maximum value. They will be subtracted. And after you do this conversion, we can implement the softmax function. So now I will do numpy.exponential x1 divided by numpy.exponential x1, and I want to sum over the first axis. I want to sum over the first axis, and it has the same problem. If you sum over it, the last dimension is, you don't have that dimension after you sum over it. So you can specify keep dimensions equal to true. Now this way, you get the softmax value. Let's say soft. This is soft. And if you try to sum over rows, you'll find that they are equal to 1. If you sum over columns, then they are not necessarily, they don't have any relationships. You are only doing row-wise softmax. So that's how you can implement softmax without overflow. All right, so that's all I want to talk about with regard to NumPy. But NumPy has a lot of other functions. I will suggest you to read the documentation very frequently. So whenever you want to implement something, you should check out the documentation to see what functions are available. If you are totally new to NumPy, it may take a while for you to get familiar to all those functions available here. But basically, all those linear algebra functions that you can think about, you can pretty much find them here. So whenever you want to do something, you can just search whether such functions are available. You can easily Google it to see how to implement something in NumPy, and someone may have already answered that in Stack Overflow or somewhere else. So the second library I want to introduce is Pandas. Pandas is another function, another library that implements basically one-dimensional or two-dimensional matrices or tensors. The difference between Pandas and NumPy is that Pandas wraps an extra layer outside of NumPy. So Pandas is based on NumPy. It still has a lot of ND arrays, but Pandas implements those indices and columns very well. So let's just see some examples. You should import Pandas as PD. Pandas deals with those table functions very well. So I would like to think about Pandas as the Python version of Excel. So whatever things you can do with Excel, you can pretty much do it with Pandas. You can create a series by s equal to pd.series. Let's say 1, 2, 3, 4. You can write anything here, and s will be like this. So s has two things. You'll notice that it shows two columns. The first column will be the indices, and the second column will be the values. So if you check s.index, it will tell you that it's ranged index. And if you check the value, I think it's value or values. Values? Yeah, those are the values that you get. So you'll find that if you check the type of the values, it will just be an ND array. So Pandas basically wraps an extra layer outside of NumPy. And this is a series. It's like a one-dimensional NumPy ND array. And if you check S0, it's 1. If you check S5, then it's 8. If you check S3, it's 6. You can do a lot of slicing as well. This will be 0, 1, 2, or you can do 3, 2, 6, which will give you 3, 4, 5. You can do slicing easily as well. You could also, so this is indexing. So this is one-dimensional Pandas data type. You can also get a two-dimensional thing here. Let's see. Let's think about what I should do. So I can, let me just create some indices. You can do pd.date range from some specific periods equal to 6. This will give you some dates from Pandas. So these are all date values from January the 1st to January the 6th. And I can create a data frame by pd.dataframe numpy.random.rand. I will just initialize some random numbers, 6 times 4 matrices. And I can specify the index will be equal to dates, and columns will just be columns. You can specify random names. Let's just call them A, B, C, D. You only need to remember that the number of indices will have to be equal to the row number, and the number of columns will be equal to the column number. So now you have a data frame. This is a data frame. It shows you that it has rows and columns. And in Pandas, we call rows as indices. So each value here will be an index. And columns will just be named columns. So if you check df.index, it's those indices. And df.columns will also be columns. So you may quickly realize that both the index and columns are all of index type. So there's no difference between columns and rows essentially. And you can easily transpose them. If you transpose the data frame, the rows becomes columns and columns becomes rows. So there's no difference. There's really no difference between columns and rows. And it provides a lot of functions for you to get access to the data. For example, if you want to get some specific values, you can do df. If you want to get a column, so df, remember columns will be A, B, C, D. If you want to get columns, you can directly write A. It will give you the first column. If you write B, it will give you the second column. And you may realize that if you get a specific column, then it will return a series to you. If you check the type of a specific column, it will be a Pandas series. But if you want to get a row out of it, then you should do df lock. I don't know why it's called lock, probably location. Then you can get a particular date. Let me just copy this date here. Then you will get the first row. And if I change that to 2, you will get the second row. And you can also specify a range. If I specify from 1 to 2, so this way you get 4 rows. And I can also specify columns. I could say A to C, and you'll get those values. So lock is a very useful function for you to get a subsample, get a subarray out of the ND array, or get a sub data frame out of the whole data frame. Sometimes if you don't want to use those named indices or columns, you can also use the value count. For example, if you do a df ilock, then you can directly use those numbers, 0, 2, 3. This way you get, I think you can realize what happens here. It gives you the rows from 1 to 3, so 1 to 3, and it gives you columns from 0 to 2, so 0th column, the first column, the second column. And you can still do Boolean indexing here as well. Let's say if you want to get all dfa greater than, let's first, if you're filtering columns, let's see what happens. If you say df.a greater than 0.5, all right, they are all greater than 0.5. That's very interesting. Let's say 0.8. Then you see some are false and some are true. So what happens if you filter them in this way? Then you only got rows where df.a is greater than 0.5. And you can also change the values of them. If you change those values to be equal to 0, and let's see what happens. Now all those columns, all those rows become 0. That's how you change some values. And you can also create a new column by, let's say, you want to create a new column E. Remember dfe, if you directly try to get the column E, then it will give you a key error because this column does not exist. But you can try to add the A column with the df B column. And that will give you an extra column E, where the value of E will be the addition of A and B. All right, so these are the basics of pandas. But a lot of time when people use pandas, they only use pandas to read some data. For example, I have some files here. I have some files that I want to show you. Let me just give you those values. So I have these files here. These are stock market data. If I open AAPL, this is Apple stock market values. You'll see those stock values here. They are CSV files, and I also have Google. They are also stock values. And if I want to read them into my, if I want to read those values here, how should I do it? I can use pandas to load them, ls data. So these are the files that I have. I will read apple equal to panda.read CSV data aapl.csv. So that's it. I can read it like this, aapl. So these values are loaded inside. But you may realize that this column, date, you probably realize that if we can change the date column as the index column, it will be great. Because if you read them in this way, then if you check apple.index, the indexes will be range indices. So these are just the integers. They are not very meaningful. So what we could do is that you can specify the index column to be equal to date. Now the indices becomes date. So another problem here is that it's probably not very obvious here, but let me show you. If you check aapl.index, you realize that these are just D-type objects. D-type objects means that they are not very special. But we know these values are actually dates, so you can pass dates equal to date. There are a lot more parameters that you can specify with read CSV pandas. I find read CSV is a very useful function when you're working with some data. So you should check out that you can specify the separator. The limiter is also separator. You can specify index column, which column will be indices, and there are some other things that you may find very useful. For example, day first. What is the format of the date, and they are past dates always, of course. So after you specify parse dates, the indices becomes date time index. So what's useful after this is that you can actually plot this stock values very easily. There's a library named matplotlib that's mainly designed for plotting data. So you can do apple.plot. This plot is very hard to read. Why? Because the volume data is not comparable with all the other stock values. So what you should do is we can only get some certain columns. For example, we can get the open data. So that's how the open stock value changes. Or we can get the close data. Or we can get all the way from open to adjusted close. How do I know the column numbers? Column names, you can check aapl.columns. So these are the columns that you can access. What's the problem here? Adjust close. Unknown date time string format unable to pass open. Okay. I think I have to specify if I want to specify columns, I have to say lock. And these are all the rows. These are all the columns. So now you have those stock values. You have open stock price, high price, low price, close price, and adjusted close price. I also have some other stock data that I want to read. So I have Microsoft and Google, and you can actually rename some columns by you can rename the adjusted close column by some other name. So I use rename columns equal to adjusted close to be Apple, and this way you get the adjusted close prices. Now I can plot it. This is the Apple stock price. Now, if I want to combine all those three stocks all together, so what I can do is you can rename each stock's adjusted close column. I just want to use the adjusted close column because I think those values will make more sense. You want to get the close stock price because that's the ending price of a trading day. So Apple becomes Apple, and Microsoft becomes Microsoft, and Google becomes Google. And these are all the stocks I need. So I have all those stocks. And you can plot them. We can plot stocks.plot. Plot. So now you can compare these three stock prices. And you also realize that Google went public on 2004, so you don't have the data before that. So if I only want data after a certain point, what can I do? So you could do this thing. We can do stocks.index is greater than or equal to stocks Google, because Google is the last stock to go public. So you can get the stocks after the first valid index. This is still Boolean indexing. Let me just break that down. If you check the stocks of Google, the first valid index will be 2004. And if you can get the stocks after that. So let's name it valid stocks. And you can do valid stocks dot plot. Now you plot all those stock values after Google went public. That's it. So that's basically it. That's all I want to talk about for today's tutorial. So this is not a complete guide to Numpy or Pandas, but it covers many aspects of these two libraries. So if you encounter any problems when you're coding with Pandas or Numpy, I would always suggest you to just Google for the specific problems that you have, and also refer to the official guides, the documentation, to see what functions are available. That's it. Okay, great. So that's the end of the tutorial. See you guys.